Hello and welcome to another session where we are going to practice some statistics. More specifically, the chi-squared tests. In this case, there are two of them. We will do the goodness of fit test example as well as a test for independence example. Now, we should have done by now, and there are previous videos on this, an introduction to the concepts, as well as an example that we do by hand. This is really another example by hand, except we're going to demonstrate how spreadsheet software can be used just to make the calculator work easier. We're not going to use all the functionality, in this case of Microsoft Excel. We're simply going to use it as a glorified calculator, if you will, to demonstrate the convenience of having space to lay out all your information and cut down on the tedium of doing things by hand. We are still doing things by hand, just in a more efficient, convenient way. So, the book we're going to use to let me zoom in here on the cover a little bit. To get some examples is the Statistics for Psychology book. You might have a different prescribed textbook. It doesn't really matter. This is just the one I have on hand. And we're going to do, get rid of this. Our number is on page 577, number 14B. So let's go 577, 14B, and let's read that together. 14, 14. There we go. Let's make it nice and big. Carry out a chi-square test for goodness of fit for each of the following studies. We're going to use a 5% confidence level. In each situation, the observed numbers are shown and the expected numbers are equal across all the categories. So we're testing if the observed numbers, we're looking at B specifically, they're all similar questions. If the observed numbers fit a uniform distribution where everything is spread equally across the four categories in our case. All right. So let's work our way through this. We take our time. You can speed up the video. You can skip ahead, slow it down, whatever you need, of course. So I have some observed values here, observed scores rather. I'll make them yellow to represent input numbers, and green are the major calculation numbers that we're going to use. So I have my observed scores, and I expect a uniform distribution. But let's calculate the total first here. We have some convenient functions built into Excel that makes it simpler, but you could start your calculation with an equal sign and say this cell plus this one, plus this one, plus this one, if you really wanted to. You can also, I'm going to delete that. You can also use a built-in sum function, and there are many other functions for convenience, and then select the cells that you want to add together, and we get our 120. The expected cell here, I calculated that as, let's redo this. I didn't know I did this. I want to calculate, let's make it green actually, because it's a calculation. Not a major one, but still. I expect the same number of scores in every category. So I expect the sum total divided by 4 in this case. I expect 30 in every category. Now I observed, of course, not exactly that. There are natural fluctuations, and we want to test, is this more extreme than I would normally get? or is this quite within the range of acceptable common variation among different samples? So I'm going to copy this. I could right click, copy and paste, or I can also click on my cell that I want to copy and hover the mouse over the bottom right corner. You see the icon changes, and then I'm going to drag it down like so. Actually, let's get a little mouse pointer going here. Let's highlight the pen. That's a little better. You can see it a little better. The problem is when I copied it like this, I double click on this to see the formula has changed because previously the cell that was referenced was the sum and I divided it by 4. Now everything moved because it was relative to this cell, this position. So when I copied it down, the reference cell moved as well, and I don't want that to move. So I'm going to go back to my original, put my cursor inside that reference cell and press F4. You see the dollar signs are inserted there. That fixes the position of the cell even when it gets copied. Enter. Now if I copy it over and double click on it, you see the cell that I'm using in this new formula is still in the same position. The dollar signs fix the position. I'll copy that all the way down and get 30 for all, of course. You see this random one at the bottom still uses the correct total divided by 4. All right. Now I want to calculate the observed score minus the expected score. So I start with an equal sign. That's a very simple calculation. Observed minus expected. Enter. Now I don't want to fix those cells because every new one should use its observed and its expected. So I'm going to select this cell, copy it down, the formula, and I can check a random one. Yeah, it's subtracting the corresponding observed and expected cells. Then I'm going to square this. So I'm going to start with an equal sign. I'm going to take this value, observed minus expected, shift 6 for the exponent calculation, and I'm going to square it. And then again, copy this formula down to the others. Check a random one. Yeah, it's squaring the right one. Hard to tell sometimes because many of these numbers are the same. Then I am going to take this squared difference and divide it by the expected number for that category. So squared divided by expected. Now we could certainly have streamlined these columns, but the benefit of having software like this is I can use my space and do little calculations on the way. We've copied that as well. And then let me just show the formula that we're aiming for. If I go way back to the front here, your book might have different looking formula sheets, but they should have, we have formula sheets available to us. We don't have to remember all these formulas when it comes to statistics. Where's my chi-squared? Chi-squared, chi-squared. Here we go. We're looking for chi-squared over here. The sum over all the categories or cells, squared difference divided by the expected. And then we add them all together. That's our chi-squared statistic. All right. So we have them all here over all the categories. We just need to add them up. That's another sum. Sum of all these guys. Close my bracket. And I get 40. Now I don't know, is 40 a reasonable chi-squared score, if you will, that I would get, sort of like z-scores, right? No, but a different distribution. Or is that very rare to get? I don't really know until I test it on the distribution and see where it sits. So we're trying to see if our sample comes from a population that fits this expected distribution, this uniform distribution, versus not. Our degrees of freedom will be 4 minus 1. So I'll just type in a 3 there. No need to get fancy. The cutoff that they gave me in the question was 5%. So let's visualize. Oopsie, I don't want the answer yet. I left the answer. Let's visualize what is happening here before we continue. Is my pen big enough? Let's see some lines here. Straight line here. Straight line there. And then let's go blue still. So we have our chi-square distribution. Now we want to see where is this cutoff so that the tail on the right is 5%. Let's put it over here. And so I'm drawing with my mouse today. What is this? Is this the right pen that I'm using? It feels very squiggly. This one. Free drawing. Yes. Doesn't matter. All of this. Let's highlight that in some way. And that's going to be my 5%. Oopsie, no, come back. I want to write 5%. I want to write it. 5. Oopsie, no, not. I'm still in arrow mode. Undo that. 5%. I get some numbers too. 5%. Boop, boop. Not very pretty. I don't have a pen today, just have a mouse. My mouse writing skills are terrible. So we want to see where is this cutoff so that the right portion is just 5%. We're going to consider that pretty rare to get. And then we'll see where does our observed score sit in relation to that, and then make a conclusion based on that. So the convenience of spreadsheet software is that it has all those statistical tables built in, but I could also look it up in my book as well. But often the book takes some jumps for presentation purposes because it doesn't have infinite pages. So using the spreadsheet function to look this up is a little bit more convenient. But I might not know what that function is called. So I have my insert function here at the top, a little f there. I can't make this very big, unfortunately. And I can search for maybe chi-squared. See what comes up. There's a whole bunch of them. Now the chi-squared distribution takes an x value and gives me the probability. This is an older version, but still. That's not what we are looking for, right? We have a probability on the right tail. We want to know what is the quote-unquote x value that gives me that. So we want to look at the inverse, and we're going to look at the right tail specifically. I press OK, and then it asks me, okay, what is your probability on the right? Well, it's this alpha, so I click on that. What is my degrees of freedom? Well, it's this 3. So let's go. And I see that it's 7.814. That is my cutoff over here. We got an observed score, which is this one. I'll just move it over so it's exactly the same, of 40. So we're sitting way out here, much more extreme than what we would expect to get if it truly fits this distribution, meaning it truly is a uniform distribution that's giving me these sample values. So we can write our conclusion. Since, let's say, chi-squared observed is greater than chi-squared cutoff, we reject the null hypothesis in favor of the research hypothesis. The evidence, so it's always nice to say your conclusion in words of the original question, sort of just more simple English words, instead of referencing a null hypothesis and a cutoff score. Someone who reads this might not, or someone who has this problem might not necessarily understand the statistics in that language. So it's good to present it sort of in plain English as much as you can as well. The evidence is strong enough to suggest that the observed score, or this, let's say sample values, let's say like this, that the sample does not come from a uniform distribution. Something like that. It's nice to have both of these versions of my conclusion. All right, that is an example of the chi-squared goodness of fit test. In this section, however, we have two of them. We also have a test for independence. So there are two different kinds of questions using our chi-square test. All right, let's go to the next problem for the test for independence example. Now, let's see, that's on page 578. Let's go to page 578, 578, and what did we say? Number 19. Let's make this a little bigger here. Come on. Come on. So slow today. Number 19. All right, let's read it together first. The following results are of a survey of a sample of people buying ballet tickets, laid out according to the type of seat they purchased and how regularly they attended. As I can see here, different types of seats and two types of attendance. Is there a significant relation? Is the seating choice dependent on the type of attendance, or does it not matter? Use the 0.05, so 5% alpha significance level. Hypothesis testing will visualize the distribution, and we'll stop there for that example, just our introduction. So I put all the information in here for our observations. Different seating, 3 different seating categories, 2 different attendance categories. So this is my observed that I'll color yellow as the input or the given numbers. We want some totals. Now we've seen before, we'll use the sum function for that. I want to add up all of these, close my bracket, enter. Then I want to copy this to the right like before, double check it. Yep, it's adding up those. I also want to add up the rows for each of the seating categories. And we'll copy that down like before. Check it. Yep, it's adding up the right two. Okay. And then we can also add up the total here if we want. Total of the totals. How many people are there? There are 260 of them. Okay. So now, how am I going to test for independence? Well, I'm going to look at the percentages, which will be how much is the row total out of the overall total. So I'm going to calculate a percentage here. Now, you could do this in a couple of different ways. Let me just make sure this is just a number format because I have tested this beforehand and I might not have changed it. Let's suppose this is some number format. I can change the type of cell this is going to be by right-clicking and clicking on Format Cells, and I see I have a whole bunch. General means it'll sort of guess what I want. I can specify a number in the decimal places. I can round it to currency and all kinds of things, date and so on. So if we want to calculate a percentage, well, the orchestra seating is 100 out of the total of 260. Now, if I just type that in, I see it's 0.38. I could multiply that by 100, and that'll be 38%. I can also set this as the decimal version of the percentage, and then format the cell as a percentage, and then it will do the multiplication by 100 for me and add the little percentage sign, which is kind of nice. Some people like that. So let's go with that. Now remember, I do have to fix the total here. So F4 inside that, because I'm going to copy it and the total of 260 stays 260. Then we will drag this down and copy the formula, all things we've done before. Check this one randomly. Okay, 40 out of 260. So regardless of the attendance, whether it's regular or occasional, the breakdown of the seating types is according to this percentage. So roughly 38% of people choose orchestra seating, 15-ish percent choose first balcony, and 46 choose second balcony, regardless of how often they attend. So now I can say, well, if this is independent, if these two properties are independent of each other, I would expect regular attendance to fit these percentages. Out of the total of 80 people, I would expect, let's do a calculation here. So this is going to be my expected cells here. So I'm calculating these, let's say make them green. So here, out of the 80, I would expect 38% to be seated in the orchestra section. I've observed 20, and then I'll ask over all of these cells, how different is this? Because even if these are independent, I expect 30.76923. I'm not getting that exactly, right? There is some natural variation. So my observed scores and my expected scores are going to be different most of the time. How different is too different? That's essentially what we're saying. So let me just check the cell again. I have the total. I'm going to fix that total for my regular attendance row, but the percentage is going to change as I move to first balcony, second balcony, and so on. So I'm going to copy this down. I maybe don't want to see this many decimals, right? I'm just going to format this cell to be a number, but maybe only a couple of decimals. I don't need that many decimal places. Just for presentation, it still remembers all the decimal places whenever I need to do a future calculation. So now I can copy this over. Let's do a copy paste this time for no reason whatsoever. And I can look at that like, ooh, it's sort of doing somewhat of the right stuff, but the cells are a little off. For the occasional people, of which there were 180, I want to use that total. So I'm going to, why can I not drag this? There we go, drag it. and make sure it's fixed because that's going to be the column total there. And I want the percentage of orchestra, expected orchestra um, seats, like so. And then I'll copy this one down, double check. Yeah, it's using the total of the occasional seated people, percentage appropriate to the row I'm in. So like that. Now I can double check myself here with some totals. I totally could. I could do the sum here of these guys and close the bracket. And I get 80 again. I get 180 again. Now I formatted that to 2 decimal places, so it continues that formatting. I can do a total here just to sort of check myself that if these totals are not the same as the original totals, then I did something wrong. So it's good to sort of check yourself like that. I can change the formatting back, but I'm going to leave it just to save some time. So important again what we are doing here. We've got some observed yellow score numbers, sample values. And we're saying, well, if I just look at the rows, I get a breakdown of these proportions, regardless of what their attendance is. So if I assume that they are independent and attendance doesn't matter, these percentages should happen in each case. So I get my expected scores here, and now I need to compare that to the observed scores. I'm just going to change this to no full. I'm worried that the green is a little dark for us to see what we're doing. So my chi-square test is the same. I'm going to look at the observed minus expected, square it, divide by expected, and add them all up. Chi-squared uh, score calculation is the same. The the slight inconvenience in this case is they're laid out a little differently. Now this is one option. I just want to make a list here so that I can calculate the sum more conveniently later. You can keep it like this, or you can lay it out all in a column like that. I chose this one, but you could have totally chosen exactly like this and did observed minus expected and have these 6 cells and then square them in a different place and then divide by the expected in a different place. But keeping them as one column or row might be a little bit more clean to some. It's personal preference how I lay this out. I still have the benefit of laying things out in a more convenient way that I can manipulate for efficiency. So I just made some row titles here. For my table, I'm going to go left top, observed minus expected. So observed minus expected, top left. And then left middle, left bottom. I can copy those over because they're going to follow the pattern. I can look, yep, that one's good. That one is also good, see. But now I'm going to switch to a different column. So I'm going to have to potentially redo this one, but it's not a problem. It's a simple calculation. Observed minus expected. I'll copy this down. Check a random one. Yep, observed, right bottom, expected, right bottom. Good. Now I don't need to sum these, I only need to sum the end ones. And I broke it down into these 3 columns for clarity, but you can totally merge this. The calculation is just more once you do that. But it's up to you how much detail you want to show, really. And we'll maybe show the variation in layout after this. So now I'm going to do the observed minus expected difference here. Square that. I don't want that many decimal places. That seems extreme. We'll right-click Format. 12. I'm good with a couple. I don't know why it gave me 12. I'll resize that cell. That seemed excessive. Copy this down. Check a random one. Yep, the cell reference is good. Now I'm going to take this squared difference and divide by the expected, which sits over here. It's green, like so. I can copy again with the decimals. Why? Let's format that. I don't know what is going on with the decimals here. I don't want that many. Let's copy these and double check. It is taking the cell next to it, dividing by left bottom. So these three sort of fit together, but I'm going to have to take the next one and that cell divided by a new column, which would be right top expected. Copy. So many decimals. I don't know. It's trolling me. I'm telling you. It is trolling me. Just because I'm recording. Check a random one. Yep, it's using the right middle. Right middle. Good. Now, let me demonstrate here just what we could have done. If we wanted to, we could have just copied, let's say this. I'm going to put it over here. Let's delete that. And we could have said, I'm just going to make this white so I can see it more easily. We could have said, okay, let's calculate for orchestra and regular, do all the calculations in one. Open my brackets, observed minus expected, close my bracket, square it, then divide by expected, like so. And then we can copy that, and we can copy it over because all the relative positions are the exact same. That one you can check uses the correct appropriate positions. That one, correct appropriate positions, and I get the same numbers as I do here, just laid out differently. And then when I do the sum, I have to add up all these, which are the same as adding up all those. So just different layouts for the exact same thing. Let's do a green here so that I can identify this cell as more important. I'm going to add them up, close my bracket, enter, 12.76. It's a rounded one presented, but if I want to be more accurate, I could see more decimals by changing the format. So let's see, where does that sit in our hypothesis test? Well, we're looking at people like the ones I've observed versus people for who the seeding is independent. And my null hypothesis is that it is independent, and those people are the same as independent people. And then my research hypothesis is no, it's not independent. They are actually related to each other in some way, and the attendance type depends on the seeding type or vice versa. There's some dependence. That these observed scores differ too much from what I expect if there was indeed no independence, if there was indeed independence. So degrees of freedom is the number of number of rows minus 1 times number of columns minus 1. So I get a 2 there. My chi-squared tail, I want 5%. Let's visualize that. Why is it so low today? Move up a little. There we go. Now my drawing skills are extremely limited. Just reset this. Actually, let's go with a line. Some straight line here, straight line there. Visualize this the chi-squared distribution like so. Not like that at all. For some reason, my pen does not want to be smooth today. Let's go slower. Slower might be the answer. It's very moody today, and I don't know why. Anyway, so I have a cutoff. Let's put it over here. And let's make it green maybe to tell the difference. This area over here, that is going to be my 5% type. Let's type. That's going to be big. I want to type 5%. There we go, like so. That's not bad. Okay. Now, we need to see where is this cutoff that has this situation that I'm looking for. Well, I'm going to go look up my function again because maybe I forgot. And it guides me through that step anyway. Now, I see that I've used this recently, so that helps a lot. It was the chi-squared inverse, right-tailed, but there's also a description to verify that, or I can search for chi-squared like I did before. So it's guiding me through, okay, what's your probability in the right tail? 5%. What's your degrees of freedom? 2 in this case. It is a 5.99 that my cutoff chi-squared score is. I have to now compare that to what I observe, but what I observe is already done up here. Maybe it's hard to see. I think you can see it still. It's up there. It's this guy over here, where we add up all of these square differences relative. So let's go back like this maybe. Yeah. So we see that, again, our observed chi-squared score is further out than our almost 6 cutoff value, meaning that there's too big a difference between what we observed in attendance scores versus what we, or attendance sample values, versus what we would expect if they were actually independent of the seating position. So let's write that up. Let's put it over there maybe, like so. And we can again say reject, like before, reject the null hypothesis because, and you can write this in yourself, because the observed chi-squared is greater than the cutoff at our significance level. The evidence is strong enough to suggest that seating, oopsie, it's one sentence, seating type and attendance type are not independent. Right? It's too extreme. If it was independent, I expect numbers around these green ones. I got numbers that differ just too much to just be happening by chance. It's because they're not, well, it's according to the evidence, suggests that it could be because they're not independent of each other. All right, there we go. That wraps up our 2 examples. A little bit longer one, this one, because we have 2 different kinds of chi-square tests, goodness of fit test and test for independence. That wraps up, like I said, our example video for today. Let me know if you have any thoughts or questions, and we'll talk again next time. Until then.